Okay, so here, let's take a look at some 3 examples on integration by parts, right? So first, let's start our first example. All right, and I want to integrate here this t squared e to the t dt. All right, so again, right, we have this here, and it's not a basic integral. Right, I can do a u substitution. So here I'll start by, so I'm going to try parts, right? Differentiate and integrate. Right, and again, my choice here is going to be if I can differentiate a function that goes to 0, I'm going to do that. So I'm going to choose t squared. And here we have e to the t. So let's start by taking derivatives, right? 2t, 2, 0. That's great, right? I get to where I want to be. And on the other side, it's easy, right? E to the t, e to the t, e to the t. All right, so plus, minus, plus, minus. All right, and then here we'll slide down those arrows, right? Last one is the integral, but that's 0. So my resulting integral is t squared e to the t minus 2t e to the t plus 2 e to the t and then again, don't forget the plus c. All right, since that last one is integral. And really what we have here is if you were to do the u dv, you would just have to do integration by parts, which we did here, right? We did it twice. It's just in the table form, so it just looks like my table is just a little longer, right? And notice here that if this were t to the 4th, we would take the same approach. We just have more terms in our result, right? But there you go. That's one approach here, a straightforward integration by parts. Now, what do we do in the case where one of the functions, or both of them, neither of them I should say, has a derivative that is tending towards 0? So let's take a look at something like this. Okay? So in this case, no matter what I choose, right, for my d, the function to differentiate, right, I'm never going to get 0. If I choose e to the x, well, that's just the same. If I choose sine of the x, well, then that's just kind of, I'm going to flip-flop between sine, cosine, plus or minus. So here's what I'm going to do. When I know that I'm going to get something that's either the same or repeats, I'm going to put them here. It's really not going to matter here. And I'm going to do these one step at a time, right? So differentiate, right, easy here. Cosine of x. Do this one more time. Negative sine of x. Okay. And I'm going to stop here. All right. So here, now it's almost like a little trick here that's going to happen. I'm going to take the same approach here, but notice in all the previous examples, I don't get 0 for my last integral, right? And that's going to be okay, all right? So I'm going to rewrite this here as the integral e to the x sine of x dx, and here I get negative e to the x cosine of x plus e to the x sine of x. Let me write this and give myself enough room here. So here, let's try that one more time. All right, so my integral e to the x sine of x is going to be equal to negative e to the x cosine of x plus e to the x sine of x. And then my last one minus the integral of e to the x sine of x dx. Now notice here, now I have an equation, right? This is equal, and here I'm going to essentially just treat it like I'm solving for e to the x. I'm going to add this integral to both sides. So I get 2 e to the x sine of x dx equals to negative e to the x cosine of x plus e to the x sine of x. All right, and then lastly, just divide through by 2. It's like a little cheat here, a little algebraic cheat that gets me to my final result. Cosine of x plus e to the x sine of x over 2. And then, as always, at the end, just add in that plus c. And that's it, right? That's how we approach something that, while one of them doesn't go to 0, we do get repeating or cycling, where we do wind up at some point with the same integral that we did before. With the same integral that we started with, I should say. All right, so that's kind of another way that we can use the integration by parts that wasn't as straightforward as some of our earlier examples. Now here is another way that we can do this. Right here, in our third example here is, I want to integrate the natural log of x. Now I know that the integral of 1 over x is equal to the natural log of x, right? I do know this, right? But that really doesn't help me here. Now I can do this integral. It's not a basic integral. I can use a u-sub, right? I don't have a formula for it yet. But I can do parts. Now here's also a different way that I can use parts. Now you may be looking at this and be like, well, I only see one function there. Yeah, that's correct. Right? There's only one function there, right? So what you can do in that case is, well, you can think of the coefficient 1 as the other function. All right? And really there's really no choice to d and I here. I must take the derivative of ln of x, because again, I don't know what the integral of ln of x is, but I do know the derivative. That is a basic one. And I want to integrate the constant function 1. All right, and then I'm going to do one step of this derivative, 1 over x, and then the integral of 1 is x. And I'll stop there. Right. The reason I stop there, and it's not 0, and I'm not repeating, is the resulting integral is a basic one. Right? It's a pretty straightforward one. So here, if I do that, the integral of ln of x dx becomes x ln of x minus 1 over x times x is just 1. And then this becomes x ln of x. Integral of 1 is just x. And as always, don't forget the plus c. Okay.